syntactic, and you will see later Thomas will talk about also reusing the context from words, from discovered words. So this is, I think, one promising track to improve the accuracy of automatic unit discovery. That's all.
Hello there, my name is Zibo. I'm going to talk to you about my work in exploring alternative inference methods. And just to remind everybody, the central goal of Bayesian inference is to learn the posterior distribution of some latent variables given some observed data. In our case, our discrete latent variables will be the acoustic unit IDs, and the observed data will be the speech features. Because the exact inference of this posterior is often intractable, we often use approximate inference algorithms. And there are sort of two main methods, which are the MCMC algorithms, which include Gibbs sampling, and the variational Bayes algorithm. And as Luca mentioned earlier, the original model by Lee uses Gibbs sampling, which samples all the latent variables and the GMM and HMM parameters, and this can be very slow and hard to scale up. So in our current model, we're using variational Bayes for the inference, and it's a lot faster than sampling because much of the computation in variational Bayes, I'll just call it VB for short, in VB can be parallelized. But this has kind of a downside that because in VB we're approximating the posterior distribution with some factorized distribution, which ignore the dependence between the model parameters and the latent variables. We can get somewhat inaccurate results and only locally optimal solutions. So therefore, I explored alternative approaches. One is collapsed Gibbs sampling, and the other one is collapsed variational Bayes. I investigated this for Gaussian mixture models just for simplicity. So I basically removed the HMMs in our current phone loop model, and I'm only using Gaussians as sort of one-state HMMs. And here's a high-level graphical model illustration of what we mean when we say we do something in the collapsed way. So on the left, we have a typical Bayesian Gaussian mixture model where we have the observed data and the latent variables, which are the cluster IDs, and the parameters for the Gaussians and the weights for the Gaussians. So when we collapse out the continuous parameters, so the weights and the parameters of the Gaussians, we obtain the graphical model on the right, where we remove those two nodes, and now we have dependency between the latent variables and the observations. So this allows us to only sample the discrete latent variables, which are the cluster IDs. And the hope is that since we're now sampling in a much lower dimensional space, we can have faster convergence and achieve better results. And this is a demonstration of the speed up from collapsed Gibbs sampling on a test data set. So my test data set comes from 9 Gaussians, 5-dimensional data. Here my model is a Gaussian mixture, just a Gaussian mixture model with a Dirichlet distribution prior, which is finite. And like in Luca's model, we have an infinite Dirichlet process or whatever prior. So as you can see in the from the plot over there, the log likelihood of the complete data for the collapsed Gibbs sampling is pretty much has pretty much converged after maybe 7 or 8 iterations, whereas for the typical Gibbs sampling, it's after maybe 20 iterations, it's still trying to stochastically catch up to the collapsed Gibbs sampling, sort of the optimal log likelihood it has found. And inspired by collapsed Gibbs sampling, we can also carry out a standard VB in the collapsed space, where unlike in the standard VB where we assume independence between the model parameters and the latent variables, now we still maintain the dependence between the model parameters and the latent variables, but we only apply the mean field approximation to the joint distribution of the latent variables. And this weaker assumption hopefully will give us more accurate results, almost on par with sampling, but also will have the efficiency of variational base. And again, here's a demonstration of comparison between collapsed VB and standard VB. And my data comes from 9 Gaussians and only 1-dimensional. I'm using the same model here. And as we can see, the curve at the bottom is for the standard VB, and we have the two curves above for collapsed VB, where I used two slightly different approximations. And again, we observe the trend that the collapsed version tends to converge faster, maybe in half the number of iterations, to somewhat of even a better solution than just standard VB. And again, this is the y-axis is the variational lower bound. And finally, I have some partial results for applying these methods to our task of acoustic unit discovery. So now my data is no longer artificial. Now it's the TIMIT corpus, where I'm using the typical train and test utterances split. And for my model, I'm initializing the maximum number of components to 600. And eventually this number drops down to about 490, 500-ish. And I'm initializing my priors with the statistics from the data. And here you observe so we don't have the VB curves yet because my VB code for multivariate data has been buggy and parallelized. So unfortunately, we don't have those curves at this time. So we have the curves for sampling for both the collapsed and the standard Gibbs sampling, and we observe that the collapsed version tends to converge faster than the standard Gibbs sampling. And just to be clear, the y-axis is the normalized mutual information evaluated for each training iteration. So for each training iteration, I label my test set with the model and perform a scoring of normalized mutual information. So I would expect the curve for collapsed variational base to climb up pretty quickly and converge to something similar to collapsed Gibbs sampling, and perhaps even better, like the plot shown by Luca in his demo. And of course, that would be faster convergence compared to standard VB as well. And to conclude, this has been an advertisement for collapsed methods, I shall say. So basically, whenever you have a graphical model with a lot of parameters and latent variables, it's always almost a good idea to try to collapse out some of the parameters and do things in the collapsed space. So the next step would be to extend our methods to the joint HMM-GMM model, which is kind of non-trivial, and hopefully that will lead to even more accurate and efficient acoustic unit discovery. Thanks a lot.